Okay, so for the 118C final review session, I think I'm gonna prioritize, and this is also 8B, the carboxylic acid section and its derivatives like the acyl halides, anhydrides, esters, amides, and nitriles. Um, is there any other chapter or topic that you guys want to go over after that?
Can you go over the carbohydrates?
Oh, carbohydrates, yeah, and also closing the ring from Haworth rejection and stuff like that, like Cherry confirmation. Okay, yeah, we can do that as well. So let's talk about carboxylic acid.
Yes.
Which is this function group right here. Right? Where R is any random hydrocarbon chain. This carbon double one oxygen here is what we will call the carbonyl. And then this OH or hydroxy group right here is what we're gonna call the LG, right? Which is the leaving group. Okay. Now, this leaving group here can be different things. And depending on what it is, it's going to give us a different functional group. But the carbonyl here will always be the same, right? So, for example, if I give you, let's say, this, 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 and this right here. We'll call these the carboxylic acid derivatives because we see that all of these, except the nitrile, will have carbon double bond oxygen, which we call the carbonyl. Carbonyl. That carbonyl is part of the LG of that one, so ignore that one. Carbonyl, right? And then these ones here that I'm going to circle in red are the LG, the leaving group, right? Where if the LG is an X, where X can be like chlorine or bromine, we'll call that the acyl halide. If the LG is a carboxyl group, we'll call that an anhydride. If the LG is another OR group, we call that an ester. If the LG is in the mean, right, it could be NH2, it could be NRH, or it could be NR2. You can have different amines there. That's going to be an amide if it is next to a carbonyl. If you see a carbon triple bond to nitrogen right there, we call this a nitrile. Okay. Now, the important thing about all of these derivatives here is that we have the carbonyl carbon here, which is electrophilic because it's attached to electronegative atoms, right? Like oxygen, halogen, oxygen, halogen, oxygen, halogen, oxygen, nitrogen. Okay. Now, I put the carboxylic acid derivatives in this specific order because going from right to left will increase the reactivity of these derivatives. So, acyl halide here is the most reactive carboxylic acid derivative, and nitrile here is the least reactive carboxylic acid derivative. Right, and that's very important to know because that'll help you figure out what reactions are going to happen. Now, I'm going to explain why acyl halide is the most reactive derivative, and let's say amide is the least reactive derivative. Okay, and it's based on two factors. The most important factor here is going to be based on the electrophilicity, or let's say positive charge of the carbonyl carbon. The other factor, which is not as important, is the leaving group ability, LG ability. So let's focus on this first factor first, the electrophilicity or positive charge of the carbonyl carbon. This azo halide right here will have the biggest partial positive charge compared to all these other carbonyl carbons. And the reason why is because if you look at this X right here, which represents a halogen like chlorine or bromine, it's the most electronegative atom. It's more electronegative than oxygen and nitrogen. So it's gonna pull or withdraw electrons towards itself, making this carbon positively charged. Another reason is that if you look at chlorine or bromine, they're like big atoms, right? Compared to carbon. So because they're like big atoms, they're in a different energy level, like a p orbital level, we would not be able to do resonance. Like that. So I'm gonna put an X here and an X here. So because we're not doing resonance as much, because this is a big atom, like the p orbitals will not overlap well, this carbon here will not gain electrons, will not gain negative charge. So that's why it would be a very big positive charge. Now, if you look at the amide over here, this amide right here will have a small positive charge compared to this carbon and carbon right here, because nitrogen is the least electronegative atom compared to oxygen and halogen. Right? If you look at the periodic table and look at the electronegativity trend, nitrogen is the least electronegative, so it cannot pull electrons as strongly as these other things. Another reason is that we see this nitrogen here, because it is the least electronegative atom, it's the most willing to donate electrons, right? Most willing to give up its electrons. So there will be a lot of resonance going on here, right? This nitrogen here is going to donate electrons to this carbonyl, having more resonance. And because this carbonyl carbon here is gaining more electrons, more negative charge, it's losing positive charge. Losing positive charge. Right. Now, if you look at this oxygen versus this oxygen, they're the same atom, so they have the same electronegativity. So the partial positive charge of those would be similar, right? Less than this one because halogen is more electronegative, but more than the nitrogen. But anhydride is more reactive than the ester because of the leaving group ability, right? If you kick off this group right here, the negative charge on this leaving group is able to do resonance, right there. Whereas if you kick off this leaving group, which I'm going to draw in red, right? Let's say all these leaving groups leaves. This is the best leaving group because the negative charge is on a very electronegative atom, chlorine or bromine. Best leaving group. If you kick off this leaving group right here, you're going to get this carboxylate ion here, which is stable because we can do resonance with the carbonyl nearby. If you kick off this leaving group over here, this negative charge on the oxygen right here cannot do resonance because there's no pi bond nearby. If you kick off this leaving group over here, we can have this amine here where we have a negative charge on the nitrogen, which is the least stable leaving group, the conjugate base, because nitrogen is the least electronegative. It cannot handle that negative charge as well as these more electronegative atoms over here. Right? So that's why azo halide is the most reactive carboxylic acid derivative, and then A- is the least reactive carboxylic acid derivative. This nitrile is a cousin, right? Because there's no carbonyl to this nitrile. There's no carbon number 1 oxygen. Now that's very important to know because these top two most reactive derivatives, the azo halide and the anhydride, and I'm going to make it lines through here like this. These two most reactive derivatives will not need acidic conditions, which I'm going to abbreviate as H+, or basic conditions, which I'm going to abbreviate as OH-, or heat to do reactions, to react. Right? Whereas the less reactive derivatives, like ester, amide, and nitrile, will need like acid, base, or heat to react. Okay. Now there's gonna be three main types of reactions that we can do with these carboxylic acid derivatives. The first one that I want to go over with you guys is gonna be reduction with the reducing agent. And then I want to go over organometallic with you guys, like the like reagents, and also the nucleophilic acyl substitution reaction. Substitution reaction. Like, and this right here will have like hydrolysis, trans-esterification, Fischer esterification, right? But I'm gonna make charts for all three main reactions. This would be the biggest chart for sure, and then these would be the smaller charts. Any questions on this introduction so far? Okay. Now we're gonna talk about reduction first. So I'm gonna erase this board right here. And then I'm gonna start making charts right now. That will help predict the product for practice problems. And also like no for synthesis problems.
Oh yeah.
Okay. So I'm gonna draw out the carboxylic acid derivatives out like this. Acyl halide at the top, anhydride second, and then carboxylic acid will be below that, which will have similar reactivity as the ester. And then carbamide below that. And then we have a nitrile, which I'm going to abbreviate as RC2.1 and like that. And then there's going to be 4 reducing agents that I want you guys to know with carboxylic acid derivatives. The strong reducing agent is going to be lithium aluminum hydride, which is LiAlH4 with an acid workup step. Now this acid workup step here could be tricky, especially with Leibniz class, because if you have an amide and you use H3O plus acid workup, the amine will become ammonium ion because we're in acidic conditions. But if you use water, then it will stay as a neutral amine. And I'll go over that when I go over to the amide, because this amide here is very like tricky with these reactions. There's a weaker reducing agent that you're going to see is sodium borohydride with NaBH4, and a second step acid workup with H3O plus or water. The other one that I want you guys to know about is dibol, right, which you can see as this. Dibol. And then the weakest reducing agent is this bulky one with lithium, aluminum, and I think it was like O3, right? And then I'm gonna make that short like this. Now, we know that these are the carbonyls of the carboxylic acid derivatives, and these are the LGs or leaving groups of the carboxylic acid derivatives. Let's look at the strong reducing agent first, where this strong reducing agent here will be able to reduce all of these functional groups. Acyl halide, anhydride, carboxylic acid, ester, amide, and nitrile. So, the acyl halide, anhydride, carboxylic acid, and ester will give the same product, which is a primary alcohol. right? So I could draw that out like this. Where if you track this carbon here of the primary alcohol, that was the carbonyl carbon. Right? And when you think of reduction, I want you guys to think of it as the reduction or loss of bonds to electronegative atoms, right? Or the gain of bonds to hydrogen atoms. We see this carbonyl here had 2 bonds to oxygen from the double bond and 1 bond to halogen. But when we use the strong reducing agent, it now has 1 bond to oxygen and 2 bonds to hydrogen. So we reduce this acyl halide to this primary alcohol. Same as for this anhydride, same as for this carboxylic acid, and same as for this ester right here. Right. Now, when you think of reducing agents or hydride reagents, you see how you have a lot of hydrides, like H here, H there, and then there should be an H at the end of it here. H here, then at the end, like there, H there. Those hydride ions are these hydrogens with the negative charge right there. And these are very strong nucleophiles or bases. Right. Now I can show you the mechanism for one of them. Like let's say we have acyl bromide right here. And I use a strong reducing agent LiAlH4. The second step, H3O+. Whenever you see lithium, think of that as sodium, right? And what charge do you guys expect to see if you guys see sodium or Li? Like what charge is associated with Na or Li? Positive charge? Yep, +1. Meaning that whatever is attached to it is negatively charged. So the negative charge atom here is aluminum, right? So aluminum is one of those weird atoms like boron, where it is going to be negatively charged if it has 4 bonds, right? Because it's at the 3rd group of the periodic table, 3rd column of the periodic table. So when aluminum has 4 bonds, it's going to be negatively charged. And this is very angry. This aluminum here is very angry. It doesn't want that negative charge at all. So one of the hydrogens is going to leave with the bond. So let's say this hydrogen is going to leave with the bond. Think of this as the hydride ion, the H- ion. This bond here with the hydrogen is going to attack this electrophilic carbon and carbon, making a new bond with the carbon and hydrogen here. But we have to top this the bond of oxygen to conserve the octet group. Right? And that's going to give us this intermediate right here. Now we have O minus. And then this is the new one between the hydrogen here. This carbon and carbon that I dotted in red is this red carbon here. If I circle this hydrogen here in red, that's the circle of hydrogen in red right there. Where this is the neo bond between that carbon and hydrogen. You could have just left that as invisible or implied, right? Now this is the tricky part here. Usually, you bring in the second step as workup to protonate the O minus into OH, right? But in this case, we will not do that because do you guys see any good leaving group present in this tetrahedral intermediate? Right. The good leaving group here is going to be the bromine, right? So because we have a good leaving group there, we won't bring in the acid right away. What we're going to do is we're going to reform the carbonyl, create the carbon double bond oxygen, and pick up the good leaving group to create our carbonyl. Specifically, in this case, aldehyde.
Well, no, but he's referring to pressure.
Yeah.
Oh.
Right. Where this red dot carbon is this red dot carbon here, we reform the carbon double bond oxygen, carbonyl. This number 2 is still there. This hydrogen is this hydrogen right here. And then we pick up the Br minus somewhere, floating there. Now this isn't safe. We don't stop here as a final product because we have excess amount of lithium and aluminum hydride. So we're gonna do this whole step again. Like this. Where this hydrogen right here is gonna go in, attack this carbonyl, push the double bond to oxygen to get this intermediate. Where this carbon here is now primary because it's attached to only one other carbon like that. That's the end of the first reaction because do you guys see any good leaving groups here? There's no good leaving group. There's no bromine, chlorine, iodine. Any good leaving group. This hydrogen here is a bad leaving group. This R group here is a bad leaving group. So we can't collapse the intermediate anymore to form carbonyl because there's nothing to kick out. Right? So because we can't kick out anything anymore, that's when we bring in our second step, acid workup, to clean up the reaction and protonate this O- and neutralize it. So I can draw that like this. Where this O- here is gonna grab this proton, and then the bond between the proton and grab and oxygen is gonna go onto the oxygen, kicking out a neutral water molecule, which will be giving us this primary alcohol here. And then you can write water if you want to. They're not kicked out. So that's why we see we have primary alcohol from reducing this acer halide right here. Notice how we did it 2 times. We used this 2 times. The first time to get the aldehyde, but this aldehyde is not safe because we have an electrophilic carbon, neocarbon, where it's another equivalent, a second equivalent of the reducing agent, you can reduce it again to get the primary alcohol, which is going to be happening as all of this. Same exact mechanism for this, and this. Well, actually not this one. This one's a little bit weird because like this one has the acidic proton, but it's going to give us the same proton, same product. And I wouldn't worry about the mechanism of this because I don't think it will be tested on the exam. The mechanism that we tested would be more likely like Claisen condensation or Fischer acidification or trans-acidification. Yeah. Yep. Yeah. Yeah, so there's 3 different types of Claisen: intermolecular, regular, and also like the mixed. Yeah, that one. Intermolecular would be if the nucleophile and the electrophile are on the same molecule. Right, so the nucleophile for Claisen is enolated, right? Because the first one is to deproton with the alpha carbon to create the negative charge. The electrophile for Claisen condensation is carbon and carbon of mixed. If they're in the same molecule, that's one molecule, and it attacks itself, that's intermolecular, it forms a ring. But if the only ion is one molecule itself, and you bring in an ester, which is a different molecule, that's intermolecular. We can go over that as well. We'll go over that as well, yeah. Yes, it's the same as that, but this thing here
Then you would have a pressure drop because then you would have to stay here, the blood would flow, it's not enough blood here.
energy drink time. Now, when you look at the amide and you use a strong reducing agent, this is easier to predict. You just completely eliminate the carbon double bond oxygen, completely eliminate the carbon neo to get your final answer, which will be this amine right here. Right? And we see that we reduced this because we got rid of 2 bonds to oxygen and gained 2 bonds to hydrogen. So that's easy to predict right there. Now this is what I was talking about when you were talking about like the H3O plus or H2O. If you use H3O plus as workup, for Liebens, the answer would be this protonated ammonium ion right there. If you use H3O plus, because the amine there is basic, it won't stay there by itself. That basic amine right there would be protonated by the acidic hydronium ion over here. But if you use water as the acid workup, for amine, it will stay neutral. Right? And that's very tricky for Levens because she will take points off if you give the wrong product depending on the acid work and stuff. Like that. Okay. Now for the nitrile, this nitrile here, when you reduce it with a strong reducing agent, it will always give you a primary amine, right? And whatever this R group is, it's gonna be this R group over here, attached to this carbon right here, which I'm gonna color code in red, which is this carbon right here. And keep that in mind because a common mistake is that when you reduce a nitrile, you sometimes add an extra carbon or lose a carbon. But this carbon here of the nitrile, the CN, is this carbon here directly attached to this amine. Okay. Okay. Any questions on this strong reducing agent, lithium aluminum hydride? Now, if we go over to the weak reducing agent, this weak reducing agent here can only react with the top two most reactive derivatives, acyl halide and anhydride. So, for here, you get the same answer, primary alcohol, and then no reaction for these right here. Because this is a weak reducing agent, it wouldn't react with the less reactive derivatives. But the two top most reactive derivatives, the most unstable ones, is able to react with the weak reducing agent to get the primary alcohol right there. Okay. So Levens also does no reaction problems as well. So when you see it on the predicted product, you see an ester trying to get reduced by sodium borohydride, there will be no reaction. No reaction. Because this ester is not reactive enough to react with the weak reducing agent. Okay. Now, when you see dibol, I want you guys to associate dibol with creating aldehydes from the lowest three reactive derivatives: ester, amide, and nitrile. Right? So I would just make a line here, here, and here, no reaction. But the bottom would become aldehydes. And this also be good for synthesis. Now this one here will react with the top two most reactive derivatives and turn the top two most reactive derivatives into aldehydes. But you most likely see it with acyl halide, but it can work with anhydride as well. Like that. Now because these are weak reducing agents, we stop at the aldehyde. We will not reduce the aldehyde into the primary alcohol like we did over here with the strong reducing agent. So this is the reduction chart that I want you guys to know for reducing carboxylic acid derivatives. 8B. 8. Oh, the last two on the right. Like, oh, that one right there. It wouldn't react with the carboxylic acid as to I don't think so. Yeah. Yeah. For 8B, you'll see the other two. Right. Yeah, the Li and the A1. Yeah, of course. Yeah. Oh, right. That's a good question. If you use H2O plus and there's still a lot of H2O plus floating around, that amine will not stay around.
Okay, so this is for H2O.
Yes, this is H2O. That's good.
How would it look for H2O?
H2O plus, this would grab a proton of H2O and become protein in H2O plus.
Okay, so if you like someone to this.
Yes. Sure. Yeah, of course. So I'm gonna update that right here. Where, like this right here, this is if we used H2O plus as the massive workup, we would actually protein amine to the ammonium ion. But if we used H2O, it would be neutral amine like that. For helix 8B, this won't matter. Like, you always get the neutral one. But for leavings 118C, this will matter for predictive products. So 8B helix, don't worry about this. This right here, with that one right now. Now that's reduction. The next thing we're going to talk about is organometallic, like Grignard reagents, organolithium reagents, which are going to do the same thing, and organocuprates with R2 copper lithium. Okay. I'm going to erase this now. Actually, I'm going to keep this side and just erase this right here. And there's only like two for organometallic. So this one is the shorter one. Shorter chart. Now we're going to talk about organometallic reagents, which are going to be R minus reagents. And there's a strong organometallic reagent like Grignard reagent or organolithium, which you will see as R MgBr, this is R prime, or R Li. The MgBr is the Grignard reagent, the Li is organolithium. Second step, acid workup, H3O plus or H2O, which would affect the product of the amide. If you use H3O plus, you're gonna over-protonate the amine to. Oh, actually, this one wouldn't matter because amide won't react with the organometallic, like for 118C and 8B. So we can actually just do H3O plus right here. Okay. Now the weaker one would be organocuprate, which is going to be R prime to copper lithium. Second step, acid workup. Now, I'm gonna draw the mechanism for an acyl halide example. Let's say we have something like this with Cl, and then we react it with first step, MgBr, second step, acid workup. Okay. When you guys see something like this, what is the electrophilic atom that you guys see in this molecule over here? The carbonyl-carbon, which is this one right here. What is the nucleophilic atom you see here on the Grignard reagent? The carbon directly attached to the magnesium. It's going to be the nucleophile. Right, and the way that I'm going to do this here is I'm going to label it or code it where the nucleophile is the star, the electrophile is the dot. So this nucleophilic Grignard reagent here will come attach this electrophilic carbonyl-carbon, making a new bond between this star and dot, between this nucleophilic atom and electrophilic atom. When that happens, the MgBr will just dissolve away into ions like Mg2 plus, Br minus. We ignore that; it just goes away, it disappears. Right? Now, when we make a new bond between the star and dot carbon, that's gonna break the octet for this carbon because like it already has 4 bonds. 1, 2, 3, 4. And when we're trying to make a new bond there, 5, that's not good. So we're gonna conserve the octet rule and pop the double bond onto the oxygen, creating a single bond O minus. Right? The reason why I star and dot this is to keep track of all my atoms so I don't like add in carbon by accident or lose a carbon by accident. Okay? So the resulting intermediate would look like this. This double bond O is the single bond O minus. This dot carbon here, this dot carbon is there. We make a new bond between the star and dot carbon because that star carbon attacked it. This is the new bond right here. The starred carbon here is attached to 2 methyl groups, 1, 2. So I'm just gonna attach 2 methyl groups on the star carbon, 1, 2. So that will help me keep track of the right carbon atoms. Now over here, do you guys think we're gonna protonate the O minus by bringing in the second step as a workout, or are we gonna collapse the tetrahedral intermediate and kick out the double bond? Which one will happen first?
You'll hear like you're gonna collapse it.
Yeah, we're gonna collapse it because we have a good leaving right here. Make a carbonyl there, kick out the double group, and get this intermediate here.
So because you're basically like the flow is like
This is the isopropyl. Carbonyl. This is the dot carbon. This is the star carbon. The Cl minus is floating around somewhere. This is not safe because we have another equivalent of the green reagent that can attack this ketone right here. Right. So we're gonna bring in a second equivalent of this green reagent here. This carbon directly attacks the magnesium with the nucleophile star, attack the electrophilic carbon, pop the bond to oxygen, get this intermediate here. This is the dot carbon, which is the dot carbon there. This is the star carbon, this is the star carbon right there. New bond, star, has 2 methyl groups coming out of it, 1, 2. MgBr here will dissolve into ions, will go away. Now, once we get this intermediate here, there's no good leaving group anymore, right? There's no bromine, chlorine, iodine. We have R groups, R, which are terrible leaving groups. So we can't reform the carbon anymore and kick it out. So then we bring in the second step, H3O+, which will clean up the reaction and proton this O minus and become alcohol. Now, the important thing here is that when you see organometallic with the carboxylic acid derivative, we're adding the new R group 2 times. Right? This is the R group of the green reagent. We added it 2 times to this carbonyl carbon. This alcohol here came from this carbonyl right here. But we added the organometallic R group 2 times. Right? The first equivalent led to this ketone. This ketone is not safe because a second equivalent of this organometallic will attack it and give it an alcohol effect. Any questions on this mechanism?
So if you still have like, if it's not written explicitly where it says like excess, and you still have that carbonyl in that like step when you attack it the second time, then do you just assume that if you have that carbonyl, you would attack it a second time?
Yeah, if it doesn't say excess or true equivalent, you would just assume that's an excess. Like that's most likely how you're gonna see it on the exam as well. Like you won't see excess or equivalent, but you get like million molecules of this and a million molecules of this. So there's gonna be a lot of those in the solution where you assume it's an excess. Yeah. So you can predict the product quickly here without doing this whole entire mechanism. Because in this acyl halide right here, we know that this carbonyl here will become an alcohol, right? And the leaving group will just go away. And we said we're adding the R group Two times. Two times. So to predict the product quickly here, this will be OH. And if we're using R prime, we're adding R prime 2 times. Right? Where this carbonyl in red right here, it's gonna be this carbonyl in red right here. And this carbonyl that I circled in blue turned into an alcohol. And these R primes are coming from the R primes of the Grignard like that. So you could basically see that we did the same thing from here to here. Without doing the whole entire mechanism, this carbon double bond oxygen is this alcohol. This red dot carbon is this red dot carbon, where we added the R groups of this Grignard reagent 2 times. And this is just copy and paste, like that. So you could do that quickly on predict the product to save time on the exam without doing this whole entire mechanism right there. It's going to be the same thing for anhydride. Right? But here's the tricky thing here. For carboxylic acid, it's different, right? I remember seeing this on my exam, and I got it wrong because I also thought this was going to be the same thing as that. But this is an acidic proton right here. And when we look at organometallics, these are not only strong nucleophiles, but they're also strong bases. Strong base, strong nucleophile. And in organic chemistry, acid-base reactions are the fastest reactions. They're faster than nucleophile-electrophile reactions, right? So we do have an electrophilic carbonyl here, but we also have an acidic proton here. So instead of the organometallic attacking the carbonyl carbon and doing this whole mechanism here, this organometallic here is going to deprotonate the carboxylic acid to get the carboxylate, right? And because we have a second step of H3O plus here, we're just going to get the carboxylic acid again from the acid markup, but we will have R prime neutral, which is R prime here, which grabs this proton, right? Which I'm gonna color in blue to keep track of where that blue thing is. This blue proton here for the R prime is this blue proton right there. This red proton here is gonna come from the second step of H3O plus. So it's basically like no reaction with this side. But there is a reaction because this is an acid, this is a strong base. Acid-base reaction happened first, instead of attacking the carbonyl carbon to get the carboxylate, and then we bring in second step, H3O plus to get that right there. If this H3O plus was not there, for leavens, this is your answer, the carboxylate ion. For helix, you assume acid workup and you get here. But he will give you full credit if you write this as well. Like this is acceptable, but on his answer keys, on his exams, he writes the neutral version because he assumes an acid workup. So this one here, I'm gonna start because I remember getting this question wrong on my exam because I wrote this as the answer because I thought that the Grignard reagent attacked this carbon here, but it does not because of this acidic proton, which is faster than this electrophile. Any questions on this so far? That's good. Yeah. Esther, same thing. This leaving group here has no acidic proton, so this could be an LG just like this and this. Amide we won't worry about. Out of the scope of 118C and 8B. Nitrile is tricky. We only do it one time. One time. And when we do it one time, we end at the ketone. Right? So this is going to be the answer. Where this red carbon here, or the nitrile, is this red carbon, no carbon right there. And we only added the R group one time. We don't bring in a second equivalent to attack the ketone to get the primary alcohol for the nitrile. So this is the strong organometallic Grignard reagent for organolithium. Now, organocuprate is the weaker one, where because it's weak, it can only react with the top two most reactive derivatives, the azo halide and anhydride. There will be no reaction for carboxylic acid, ester, amide, and nitrile. Yeah, no reaction. It only reacts with the top two most reactive derivatives, azo halide and anhydride. And because it's weak, we only do it one time, where we end at the ketone. Now, even though the reagent has two R primes, only one of the R primes will attack, leading to the ketone. Only one time. Okay, so this is the organometallic chart for carboxylic acid derivatives.
AB doesn't work.
This one?
Yeah.
Oh, okay. If you haven't seen CuLi, then don't worry about that for Helix. Yeah.
Okay, and then you put the dash like no reaction.
Yeah, the dashes here for amide is gonna be no reaction, especially for the organocuprate.
Okay.
But this one here is gonna be something else taught in Chem 131. 131. Yeah. Yeah, so you know an organometallic is a strong base and a strong nucleophile. And in organic chemistry, acid-base reactions are the fastest reactions. So the carboxylic acid here has an electrophilic carbon-carbon because it's positively charged. Oh wait, no, yeah, this one right here, an electrophilic carbon-carbon because it's positively charged, and an acidic proton. So there's a competition here. The organometallic can either attack the electrophile here, pop the double atom oxygen, doing this whole mechanism, leading to this product, or it can do an acid-base reaction where this organometallic will deprotonate this carboxylic acid, leading to the carboxylase. Right. And because we said acid-base reactions are the fastest, it's gonna go for this proton. Right. So an arrow we drawn here, grab the proton. The bond between the hydrogen we grab the oxygen will go onto the oxygen like that, giving the oxygen a negative charge. Now the next chart that I'm gonna give you guys is the biggest chart because that's gonna talk about like how to convert to this, or this, and how to go backwards to carboxylic acid. So I'm gonna need like smaller boxes here. But any questions on this so far before we move on to that one? Okay. That's good. Okay. This next set of reactions is going to be nucleophilic acyl substitution. Yeah, so you know how this carbohydrate when it attacks this buffer, the empty product disappears. It dissolves into ions. So this arrow is important to this ion. Nucleophilic acyl substitution, and this can be done in neutral conditions, acidic conditions, or basic conditions with heat. Right. Let's start with the most foundational one, hydrolysis. When you see the word hydrolysis, I want you to think of water, H2O. Right? So, I'm actually just gonna write all the reagents here and then explain it as I go on, but
Wait, what does the NAS stand for?
nucleophilic acyl substitution.
Also, expand one
Okay. So, this is acyl halide, anhydride, carboxylic acid, ester, amide, and nitrile. We're gonna first look at neutral water, no acid, no base, no heat. If we have just neutral water here, which is stable, not reactive, which one of these do you guys think is gonna react with just water alone? With no, yeah, the top two, acyl halide and anhydride. Right, this one would be no reaction, no reaction, no reaction, no reaction. Okay. No reaction, all three are like that. Okay? What this will do is that this will convert the top two most reactive derivatives back into the parent functional group, carboxylic acid. This is the parent, all of these are derivatives of this parent. Right, so that's hydrolysis right there.
That's not what it's saying.
This OH here is coming from the water. Now, if we have water in acidic conditions with heat, now this acid and heat here will allow the esters, amides, and nitriles to react. Right, this carboxylic acid here is already a carboxylic acid, so you can say no reaction, or you can draw in the carboxylic acid. But it's already a carboxylic acid, right? So this it will still be the same. This will still be the same. And now, the ester, amide, and nitrile can be hydrolyzed into the parent function of the carboxylic acid as well because of the acid in it.
That's like two.
This C right here of the nitrile, which is in red, is the C right there. Now, if we have basic conditions and NaOH in water, we will do the same thing for all of this. But if we see over here in the carboxylic acid case, the base will deprotonate this acid, leading to a carboxylate ion, like this. Because this is a strong base, which will deprotonate this specific proton, so you get the carboxylate. We still do hydrolysis with the top two to get the carboxylic acid here. Ester, the same as well.
Tablet because you're consumed first.
Amide,
So then the things will be wasted.
and also. Now, if you had a second step of H0 plus, you could turn this back into the carboxylic acid for leavings. But if there's no second step, it's just base, then you have to deprotonate the carboxylic acid into the carboxylate.
It's not that. I don't think it's
And let's say this is R prime right here. Now we're gonna start getting to this concept where
oh shit, it starts at 30.
the most reactive carboxylic acid derivative, the acer halide, can make any of these derivatives in one step. It cannot make this nitrile, right? Like this acer halide here can make the anhydride in one step. It can make the carboxylic acid in one step. It can make the ester in one step, or it can make the amide in one step. But if we look at the ester over here, right? This ester can make the amide in one step because it's more reactive than the amide. But it cannot make acer halide in one step because the acer halide is more reactive than the ester. Okay? So we're gonna start looking at the acer halide reactions where we're gonna make all of this in one step. If we want to make the anhydride in one step from the carboxylic acid, we basically have to use the Lg of this, which is this carboxylate ion over here. Where this circled carboxylate ion over here is this circled carboxylate ion over here. Now, this one here, the anhydride can make another anhydride by using that same reagent. That's why I added the R prime there because that R prime would be different than this R over here. But I barely see this reaction, so I wouldn't worry about this. Here. So that's going to be this right here. Now, when we see this carboxylic acid over here, this would be no reaction going all the way down here. Because we see the anhydride is more reactive than the carboxylic acid. So this carboxylic acid cannot make this anhydride in one step. So there should be no reaction for all of this because all of these are less reactive than the anhydride. Right there. Like that. Okay. Now, if we look at the neutral alcohol with no acid, no water, only the top two most reactive derivatives can react with that neutral conditions. Everything else would be no reaction. Right, so I'm just going to write the no reactions for all of these less reactive derivatives for the ones that have conditions.
Yes, you did. You said sit down.
neutral alcohol here can only react with the top two most reactive derivatives, acyl halide and anhydride. So there would be reactions for these, converting them into esters. Like that. Now, if we put acid and heat, it's gonna be able to react with all of these derivatives now. Right. Now, nitrile is the weird one because nitrile can only do hydrolysis to get into carboxylic acid. So there will be like no reaction for these nitriles here. NR, NR. Right. So for when you see nitrile, it can only be converted to the carboxylic acid. Right here, or you can do the organometallic like Grignard reagent to add one R group to the ketone, or you can do reduction with a strong reducing agent to get the amine, the primary amine. Now, all of these are alcohols.
Also, the arterials that are regulated.
Same as for basic conditions. Except, if we're in basic conditions here, and we reacted with this carboxylic acid, what would happen instead? It would do an acid-base reaction. It would deprotonate the carboxylic acid into the carboxylate in basic conditions. This OR minus here, it can either attack this electrophilic carbon or acidic proton. So because acid-base reactions are faster, the base OR minus will deprotonate this carboxylic acid into the carboxylate instead. So that's why this right here is the starting one, because like any base put into this acid would be deprotonated to the carboxylate. Base NaOH, base NaOR. This one would be. Now, because this is a R primarity, I'm gonna say that for here, I'm gonna put R double prime. R double prime. To make them different R groups. Okay? Because we see this is R prime, this is R double prime because of that OR group right there. Oh, this is very Now this right here and this right here will actually be no reaction. Because you guys see how this is an amide right here, which is less reactive than this ester. We cannot make an ester from this amide in one step because the amide is less reactive. So this would be no reaction, and this would be no reaction as well. Because we cannot make this ester from this less reactive amide right there. And the reason why is because if you think about the mechanism, we have, like, let's say, an OR minus floating around. If we kick that out, we're going to kick out a voice leaving group, NH2 minus. We don't want to do that, so that's why there's going to be no reaction. Now, in neutral conditions, amine with excess or T or pyridine base will convert the most reactive derivatives into amides. Now in basic conditions, same thing. For the top two most reactive derivatives. Now, in basic conditions here, with the NH minus, we're gonna deprotonate the acidic carboxylic acid into the carboxylic ion. Because the ester is more reactive than the amide, we can make the amide in one step with the base and yeah. Now when you see this base right here, that amide will just get deprotonated by the strong base. Right? Because this is also an acidic proton right here. Acidic proton.
High surface area. That's great. So each person
No reaction. No reaction. Now, when you see SlCO2 or PbR3, that's going to convert the carboxylic acid into the acyl halide, the most reactive derivative. When you use SlCO2, you create the acyl chloride. When you use PbR3, you get acyl bromide. Yeah. So the important concept to know here is that the more reactive derivatives can make the less reactive derivatives in one step. The less reactive derivatives cannot make a more reactive derivative in one step. Right? Yeah. The more reactive derivative can make any of the less reactive derivative in one step. Right? But the less reactive derivative cannot make any of the more reactive derivatives in one step. Right? So for example, if I gave you this acyl bromide right here, and I react this with this ethanamine with T, triethylamine, what would the product look like here? What would be the reaction here?
I think I might.
So we see in the reactant we have an acyl bromide, which is this right here. On the reagent we have a neutral amine with T, which is this one right here. So if we go see that, we're going to make an amide. Right? And to quickly look the product quickly here, this Br is the Lg. We're going to substitute that Lg with this whole entire thing minus one hydrogen. Like this. Nitrogen, which is attached. One hydrogen and an atom. This red. What was that? It's like we basically substitute this individual bromine into this amide using this neutral amine right there. We were able to do that in one step because this acyl halide here is more reactive than this amide right here. Right? But let's say we try to do the reverse, like this. Like let's say we started with this amide right here. Like this. And we try to create this acyl halide right here. There's no reagent that would convert this amide into this acyl bromide in one step. We cannot do PbR3 here because this is not a carboxylic acid. Right? If you look at the amide reactions here, there's no reaction that would create an acyl bromide. But we can still do this in the synthesis problem. Right? So let's do retrosynthesis here. If we go backwards, what reaction do you guys think happened as the last reaction in the synthesis here? Yep. We could come from a carboxylic acid, OH, and we could convert this carboxylic acid into this acyl bromide using PbR3. Now, how can we create the parent function for this amide here? We could do that through hydrolysis. Yep. acid, water, and heat, which is going to be H2O, H2SO4, and heat. So amide or any carboxylic acid derivative with acid, water, and heat will always get into the parent functional group carboxylic acid. And then once we have this carboxylic acid, we can create the acyl bromide using PBr3. And then once you have this PBr3 right here, you can do all of these reactions. Like once you get this, once you get this acyl bromide right here, you can do all of these reactions right here. So that's good for synthesis because this most reactive derivative here can do all of these reactions. So when you start with any of the less reactive derivatives, you can hydrolyze it to the parent functional group, which can then be converted to the highest reactive derivative using SlCO2, PBr3, which can then do all of these synthesis. Now there's other carboxylic acid derivative reactions like Hoffman rearrangement, HBZ, Helvor-Zielinski reaction, amadation, like enolate SN2 alkylation. So those are like the three other ones that I'm going to go over after this here. But there won't be a chart for those ones. Yep. For the nitrile, for this one right here, this will be no reaction. This one?
Like second class. Yeah.
What is this? No reaction. No reaction as well. No reaction. So no reaction, no reaction. Except when we get into hydrolysis, converting it back to the parent function group. So you guys notice how when we get to the less and less reactive derivatives, they can do less and less reactions. Okay, less and less reactions. When we go up the reactivity list, they can do more and more reactions. So in synthesis, it's best to get to here if you're working with integration with all of this here. And to do that, you can use the SlCO2 PBr3 from this carboxylic acid. And all of this here can convert into this carboxylic acid using hydrolysis with like acid, water, and heat, for example. Acid, water, and heat. I kind of forgot the reagents for Hoffman rearrangement and HBZ, but I'll try to remember it, and then you guys can help me as I go over them. I'm gonna erase this now, and then go over those three reactions, and then do a couple of synthesis problems, and after that, I want to go over Claisen condensation, like the self one, the mixed one, and the intermolecular one. And then after that, we'll end up with carbohydrates like Haworth projection, Cherrow concentration, Fischer projection, how to close them up, how to open them up. Because yeah, that's going to be for both 22C and 8 Claisen condensation and sugars. let's talk about hell. Zelensky. HPV. Reaction to this. So what this will do is that this will start with a carboxylic acid. And that will create an alpha brominated carboxylic acid
Yeah. And then a normal,
with,
they're
I
supposed
think,
to,
P trace
they're supposed to fight the Kalmar. Something is supposed to
BR2.
Kalmar.
So, for example, if we have this carboxylic acid right here,
End up fighting Kalmar.
where this is the carbonyl carbon, and the first carbonyl attached to it is the alpha carbon, the second carbon attached to it is the beta carbon, and we use P trace
But it also does
BR2. Make sure that the alpha carbon has at least one proton, because that one proton will be substituted with the bromine. Like that, right? Where we brominated the alpha carbon. So that's HBZ reaction right there. There is a mechanism to this. I forgot the mechanism, but for Liebens, you could write that mechanism on the note card and just do that. Helix as well for 8B. Now, the next thing is going to be Hoffman rearrangement. I don't know the mechanism for this as well, but I know that there's a weird migration step for this mechanism. So be careful of that migration step. Right. And this is going to start with the primary amide and get a primary amine. And this reaction here is very powerful because it will lose one carbon. That one carbon will be in the form of carbon dioxide, CO2. So in synthesis, when you see one less carbon and you're working with carboxylic acid derivative chemistry, know that you're going to do a Hoffman rearrangement. And the reagents for this are going to be NaOH, Br2, and water. So for example, if I have something like this, and I react this with NaOH, water, and heat. Wait, no, I was thinking of something else. NaOH, Br2, water, and Br2. I'm gonna get this product right here. Right, where this entire primary amide right here will be converted or transformed into this amine right here. And we see that this carbon of the amide is gone. It's not there anymore in the product. That carbon right there went away in the form of carbon dioxide, CO2.
also yourself.
Now the last reaction for this section is going to be like imidation. And that's going to be like, let's say we have this amide right here. And we react it with the strong base, like Na, NH2, NH3. Right? It could be NaOH as well. Or NaOR. And second step, you see a halo alkene like that. This is an amide right here that has no acidic protons because this nitrogen here has no hydrogen attached to it. So there's no acidic proton there. The most acidic proton here would actually be the alpha proton, right? Which is coming off of the first carbon, attached to the carbonyl carbon. So the strong base here, whatever we had, like I say NH2 minus, like there's no heat, so we won't do any other reaction. We'll deproton this alpha proton and make an enolate ion.
You need a force to like
Now, when you see this enolate ion over here, the nucleophile is not this O minus. The nucleophile is actually this alpha carbon here with the star, because when you do resonance, right, you're gonna get this resonance structure right here.
oh, this is along the
Where we see that there's a negative charge on the oxygen for this resonance structure, a negative charge on the alpha carbon for this resonance structure. And which negative charge do you guys think is more stable? The negative charge on the oxygen or the negative charge on the alpha carbon? Which one is more stable? Yep, this one's more stable because oxygen is more electronegative than carbon is. And because it's more stable, it's less reactive, less nuclear philic. And carbon is less stable because it's less stable, it's going to be more reactive, more nuclear philic. So that's why I started this alpha carbon here as the nucleophile. Now you could use either resonance structure to do the second reaction, which is SN2, right? So let's just use this one here that I drew out to this group bond right here. Electrophile right here. This will attack this carbon because of bromine, and that would alkylate the alpha carbon. Add an alkyl group.
either on both sides.
This is the star carbon. This is the dot carbon. This is the neo bond between the star and dot carbon. The dot carbon has methyl group attached to it. This is that methyl group right there. The bromine got picked up as a leaving group. What this did was that it added an alkyl group to the alpha carbon right there.
Higher pressure to low pressure. You're going from
So when you push them, you change the motion coverage.
Ties in consistency, fixture acidification, transpacification, the intermolecular ones, especially, like forming the rings or breaking up the rings.
unless you add
Yeah. Right. Mutuum 3, like the sugar, the new material, like sugars, amino acids, less mechanisms there. Mechanisms will be more likely mixing the mutuum problem. Now we're gonna use like all of the reactions we learned for the carboxylic acid derivatives, reduction, organometallic, NAS, and these ones to do synthesis problems. Put it all together.
in order to balance basically like if we were to imagine it's just a capillary.
So the nucleophile,
Out of your depth. You have to balance it by on the other by yeah, right. So that pressure is
Right. So LPA is a strong base. So if you're comparing the acidity to the you gotta look at the concentration. If you decrease this hydrogen, you get a negative charge. If you decrease this carbon, you get a negative charge. The negative is more stable than
you're
because you can do this.
filtering type.
That's what this negative structure is.
Yeah, positive.
No. So this is you remove the alpha. Oh no, you get the alpha carbon to the carbon. Yeah. Yeah. Because that is more stable than the other one. let's give you guys a couple of synthesis problems here for you guys to put all of these reactions together, and then we'll do Kaizen really quickly. I'll give you guys three to try. We'll increase the difficulty of these. So this is going to be the easy one. 2 is going to be the medium one. 3 is going to be the hard one.
This is what I did. Try these three synthesis problems, and then I'll walk around, answer any questions you guys have individually, and then I'll go over these synthesis problems at the end. This are a cyclic heat, right? Which is equal to so when we reacted with NaOH or heat, and then we right, so but it's not like that's it's gonna be O minus, right? So the way that this is the bond with carbon they will not be they will not be so yeah. So the reason why she did that is because she was asking so she wants
Animal Farm, yeah. No, I'm well,
yes.
Animal Farm, yeah.
Oh, if you did synchronization there, you would get that. But you don't raise that's another key. This is your mission.
Right, no. Basically, it was just like this guy that it's just basically like it's like he's like performing. Like it's like the whole performance. My
Like, are we supposed to be using the table that you do?
that table and also there's other reactions that
Is this synthesis?
this is synthesis, yeah. But in B helix, like he also doesn't know this, yeah, let me see. Yeah, like helix covered all the reactions here. But I'll show you why it's not the process, why it's and that might
Would it be this or like, because I was looking
like the reactions. Yeah, so it would be actually that, this, and that. Right. There's a way where you can think about it, which is gonna be which is only back. And now it's making this. Yep, that's right. I didn't go over that, but I can go over that. That's one route. But there's another route where you don't need to do a line over that. You can just get that by using all the reactions. And I'm going to go over this now. Which one do you guys want to go over? Carbohydrates. Yeah. Okay, let's do this is problem, and then go over carbohydrates. So for synthesis problems, the first thing I do is find my similarities between this reactant molecule and product molecule. So the word that I'm going to number this here is, I'm going to number this 1, 2, 3, 4, 5 to show that that exact 1, 2, 3, 4, 5 is this 1, 2, 3, 4, 5, like that. Okay, now I look at the differences between the reactant molecule and product. This reactant molecule has a bromine on carbon 4. This product molecule here has ester on carbon 4 directly. So we know ester is one of the carboxylic acid derivatives, right? So we could do retrosynthesis here, meaning that we could go backward. If we go backward here, if you guys had to guess, what did this ester come from? What functional group? What is the parent functional group of carboxylic acid derivatives? We could say that that ester came from a carboxylic acid, the parent functional group of the derivatives like ester, amide, acer halide, and hydride. The parent one is the carboxylic acid, so we could say that that ester came from a carboxylic acid like that, where this hydroxy group just got converted to this OR group right there. And what reagents do you guys know that can create this ester from this carboxylic acid right here? Let's do acidic conditions. Acidic conditions. Right. So we're trying to substitute this OH with this OR group, and to do that, we could just copy and paste this entire OR group into alcohol like this, isopropanol, and this and this in neutral conditions would not do any reaction because this is the less reactive derivative. We need acid and heat as well. Acid and heat, which will convert the carboxylic acid into an ester. And this has a very specific reaction into it. This is Fischer esterification, because we started with the carboxylic acid and we made an ester at the end using alcohol, acid, and heat. Right. So this is also part of the chart that we went over for the NAS chart. When we start with the carboxylic acid, we can create an ester using ROH, alcohol, acid, and heat. Right. Okay. Now this is 118A right here. Can you guys think of steps to convert this halocane into this carboxylic acid right here? This is also 8B with 8B reactions. 118A and 8B. Where do you guys think this carboxylic acid came from?
Acyl halide.
SN1. So we are gonna do a substitution, which is like SN1, SN2, right? But we see here this bromine here can get converted into an OH using not SN1 but SN2. Because you know how for SN1 mechanism we form a carbocation intermediate, we cannot form a carbocation intermediate here because it would form we can because it's concerted, but the better way would be SN2 with NaOH and water, because the OH minus here will attack this carbon, take that bromine out to get this primary alcohol here. Right. Now, once we have this primary alcohol, this is a 1,2,A reaction or 8B reaction. How can we convert this primary alcohol into this carboxylic acid right there? Right. Did we oxidize or reduce this primary alcohol? Yeah, we oxidized because we saw this carbon here gained 2 bonds to oxygen and lost 2 bonds to hydrogen. So we want to use an oxidizing agent. Do we want to use PCC oxidizing agent or Jones oxidizing agent to convert this primary alcohol into this carboxylic acid? Jones, right. Jones. If you use PCC, you get an aldehyde, but we don't want an aldehyde. We want a carboxylic acid to then do Fischer esterification to get the ester right there. Right. So to summarize, SN2, oxidation, Fischer esterification. So this is the new reaction, Fischer esterification. These are old reactions.
At the very end.
Yeah, so that has extra energy right there. Like this.
Now, for this next synthesis problem here, let's use the same strategy. The similarities is going to be this right here. Like 1, 2, 3, 4. 1, 2, 3. And then we see in the reaction we have a nitrile. And then on the product we have a amine.
That's what they need to get.
Now, look at carbon 3. Carbon 3 here is the carbon of the nitrile, right? For the reactant. And then the product, carbon 3, is the carbon directly attached to the amine. What do you think was this carbon 3 somewhere in the middle? Like what do you think this carbon 3 was? What functional group? Nitrile is a cousin of the carboxylic acid derivatives. What is the parent of the carboxylic acid derivatives? Carboxylic acid, right? So how can we convert this nitrile into the carboxylic acid? Like this. Yep. H2O, H2SO4, and heat. This is hydrolysis right here, which will convert this nitrile into this carboxylic acid right there. Now, you know how in the product here we have an amine? Let's say there was a carbonyl over here, and we go backwards. What reaction do you know that would reduce this amide into this amine right here? What reagent would do that? This is from the reduction chart that we went over earlier. Yeah. Yeah. Lithium aluminum hydride, the strong reducing agent. Great. What see that? Lithium aluminum hydride. Second step, to be specific for leavings, I'm gonna use water because if I use H3O plus, this would be ammoniumide. Right. Now, we could technically do this in one step, but that's not very clean for synthesis. The cleaner way is to, because like, you know how this is a less reactive molecule, we would have to add like acid or base with heat, which is very messy. How can we get the most reactive derivative, acyl chloride or acyl bromide, from this carboxylic acid?
And so what that does is because you're
Let's say we use SlCO2.
increasing volume, oils also
That would convert this carboxylic acid into this acyl chloride right here. And then once this is the most reactive derivative, like we went over with the NAS chart, it can create any of the low reactive derivatives once it's done. So we see here we wanted to create this amide from the acyl chloride. So to do that, copy and paste this entire group, which is an ethanamine,
portal space. Yeah,
and T, triethylene. That would convert the acyl chloride to the amide in one step. And then from there, we just use the reducing agent to reduce the amide to the right there. So to summarize this one, first reaction, hydrolysis to hydrolyze the nitrile into hydrolysis into the carboxylic acid, and then this is like SN2. But it's not SN2, but it's like SN2 like to substitute the OH to Cl, and this is like NAS, like one of the NAS reactions to convert the amide into, the acyl chloride into the amide, and this is reduction, where we reduce the amide to the amide.
so this is like your diagram. So this is kind of like what happens when your diaphragm she's gonna pull down on it.
You don't have to always use heat for first acidification. Yeah. You can see some problems with just acid and alcohol, and then it can still do first acidification. Yeah, but it will increase the reaction rate if you add heat. Yeah. Yeah, of course.
Is like intraportal space, space that's not.
Okay. So for this next synthesis problem over here, let's do the same technique or strategy. Find a similarity first, which is gonna be, I'm gonna highlight it in red, like this, which is this red part of the product right here. Now the reason why I erased that red bond right there is because we see that we just lost a carbon. That carbon was there before, but now it's no longer there. So the difference here is that here we have an ester with this one extra carbon, and here we have a methyl group and an amine group like right there. Okay. So if you see the loss of one carbon, what reaction do you guys think of? Yep, Hoffman rearrangement. And what is the reactant of Hoffman rearrangement?
It's 210.
The reagent would be NaOH, H2O, Br2. But those are the reagents. What is the functional group that we start with for Hoffman rearrangement? Primary amide, right? So we're gonna have to do Hoffman rearrangement somewhere in the synthesis. But before we do that, you know how there's a methyl group here at this carbon, which is this carbon right here. If this is the carbonyl carbon, this is the alpha carbon, right? And we could alkylate the alpha carbon by doing enolate chemistry, right? So you know how when we did amidation, we had to like work with an amide here. We could also do the same with an ester. So what can we use to make this carbon negatively charged? Right. What can we use to make this carbon, alpha carbon, negatively charged? I'll give you a hint. I'll draw this out. What can we use to grab this hydrogen here? Any kind of base. Let's use a strong base, like NH2 minus, right? So from here to here, first one, and H2 minus. Nucleoide solvent, ammonia. That would deprotonate the alpha proton, give that alpha carbon a negative charge, which is the nucleophile star, and then we can use CH3I where the negative portion of the carbon here is find this methyl group, pick up the negative group, to then get us this right here. Like that. Right? Where if I starred this carbon here, that's the star carbon. If I dot or this C0 right there, that's the C0 right there. And this is the neo bond between the star and dot right there. So that's how we get the methyl group over there. Any questions on this part right here? Now, when we want to do a Hoffman rearrangement, we want to make this into an amide. What is the clean, best way to convert this ester into an amide with no, like, let's say, messy conditions like acid, base, or heat? How can we convert this ester into an acyl halide, like an acyl bromide or acyl chloride?
Alveolar pressure. That's what causes.
Yeah, we can use SlCO2, but SlCO2 would work with carboxylic acids. So how can we convert this ester into the carboxylic acid first?
We just do hydrolysis.
Yeah, we can do hydrolysis like what we did over here with water, acid, and heat. So let's do hydrolysis with water, acid, and heat, which will convert this ester into this carboxylic acid, the parent functional group. And then from here we can do SlCO2 with like T or pyridine to convert that carboxylic acid to the acyl halide. And then to create the primary amide, we can use ammonia and T. To get this primary amide. Now once we have this primary amide, we can do Hoffman rearrangement with NaOH, H2O, CO2 to get the primary amine where we lose one carbon. So where was that? This amine here is this amine. Now this amine here is this part of the amine here, but we see that there's a carbon when you go here creating the amide. And to do that, we could add in this entire group as an acyl chloride with T. Right? So this acyl chloride here will react with this amine and T to create this amide right here. So I can code it like this, where like this structure in red right here is this structure in red. This structure in blue right here is this structure in the leaving group chlorine just leaves. Like that. So you're used to seeing acyl chloride as a reactant and amine as the reagent, but you don't always have to see it like that. You could see the amine as the reactant, and then you could see the most reactive derivative as the reagent. Right? So to summarize, the first reaction here is enolate alkylation.
No, we did the variant.
Right, we first formed the enolate ion by doing acid-base reaction, and then we alkylated it by using SN2 reaction. Second reaction here is going to be hydrolysis to convert the ester into the carboxylic acid, and then we did like SN2 like reaction, and then we did NAS to convert the acyl chloride to the amide, and then we did Hoffman rearrangement.
Yeah, I got this one.
I guess you forgot.
And then we did another NAS here, where the most reactive derivative reacted with the amine with the amide. So this one here was 1, 2, 3, 4, 5, 6 steps for this synthesis here.
Oh, so
3 steps, 4 steps, 6 steps. Yep. Yeah. Yeah, so this MgCO2 here is a method to add an extra carbon. So that would create that right there, but then it would like create a carboxylic acid, not an acyl bromide, but it would be like this right here. So we have, yeah, that. like that instead. Yeah, yeah, yeah. First. Oh, you guys just finished all the practice. Yeah, that's yeah. Okay. Now I want to go over how to close Fisher projections into Howard projection and chair confirmation really quick, and I will end the session there. There's also a way to go backwards, but we won't have time for that. But I will have like a 4-hour final review session tomorrow morning, 7 a.m. to 11 a.m. If you guys are interested, like it's gonna be on here. If you guys are interested for that, yeah. But we'll just end up with the sugar opening reaction, closing reaction. Okay. Any other questions on this so far? Okay, let's skip. Now there's aldose and ketones, and you can make it pyranose, a 5-membered ring, or pyranose, a 6-membered ring. And then the 6-membered ring, you could create a Howard projection or chair confirmation. And then there's like alpha, beta, and enantiomer when you close the ring. So I'm gonna start out with the most simple example first, and then we'll build on to the ketone example. So let's say we have D-aldohexose, generic one. D-aldohexose. Right. Okay. Let's say we draw D-glucose, which is a type of D-aldohexose. D-glucose. So aldose meaning tro, aldehyde. C is at the bottom. D sugar, so the last carbon will have alcohol at the bottom, right? And then it's hexyl, so it's 6 carbons long. 1, 2, 3, 4, 5, 6. And then the alcohol and hydrogen here can be in different configuration, right? For D-aldohexose or D-glucose, it's going to be specifically this here. Like that. Okay. Now, helix doesn't make you memorize D-glucose structure. He'll just say D-aldohexose, or he'll give you the structure. But Levens will expect you to know the Fisher projection of D-glucose, which you can write in your note card, or to say based on your note card. There is a trick where you can memorize this exact configuration of D-glucose, right? So look at these horizontal bonds right here, right? And then use your right hand, right? And then those 4 horizontal bonds right there are going to be these 4 fingers right here, right? And where the alcohol points to is where your finger is going to point to. So this is your index finger, your middle finger, your ring finger, your pinky finger. So alcohol on the index finger goes to the right side, left side, and right side like that, right? So this is how you can remember D-glucose, where your finger points to is where the alcohol points to. So this is D-glucose right here, using your right hand, like that. So during the exam, if you want to try D-glucose, just do this on the exam, and then you can draw D-glucose like that, right? Or you can write on your note card, if you want. Right? Now, this right here is the Fisher projection, the open linear form, which is not very stable in nature. In aqueous solution like water, it's going to close to a ring. And let's say we want to make a 6-membered ring. And to do that, right, I'm going to redraw the tro into this aldehyde right here, like this. This carbonyl carbon, yeah, that's what it is the electrophile. because it's partial positively charged. And we are going to call this the anomeric carbon, right? Because they're going to lead to two different elements. If I want to make a six-membered ring, I gotta make sure that this atom pair, which I'm gonna label as number 1 when I attack that carbon, has to like go to the 6 atoms to the nucleophile. So let's say that's 1, this is 2, this is 3, this is 4, this is 5. The official nomenclature will refer to this as C6, which is correct, but the way I'm numbering this is not gonna be the official nomenclature. It's just gonna be how I close the ring. This cannot be number 6 because this cannot be the nucleophile. There's no pairs of electrons of this carbon that can attack this carbon here. This hydrogen cannot be the nucleophile because there's no pairs of electrons to attack this carbon carbon. This oxygen here can be 6 because that oxygen there can be the nucleophile with 2 pairs of electrons, like that. Right. Now, before we close the ring, I want to make sure that my 1, 2, 3, 4, 5, 6 is going straight down like that. Right now, it's not going straight down. It's going down and then going to the right at the end. Right. And to do that, I'm gonna have to rotate this single bond right here and rotate these 3 gears. If I want to make the 6 at the bottom, I'm gonna make sure I rotate everything clockwise, 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 and clockwise, like that. Right? That would rotate these 3 gears like that, keeping everything up here stationary, the same. So I'm just gonna redraw this because this is the same structure, just redrawn like this. Or the bottom 3 is gonna have OH at the bottom because we moved it down there. CH2OH at the left side and H at the right side right there. Everything else is gonna be copy and paste. Like this. 1, 2, 3. OH. And H. Where this is gonna be 1, 2, 3, 4, 5, 6. That allows our numbers to go straight down like that. Okay? And the reason why we do this is because that would allow us to tell what direction will our alcohols go to. Will it go up or down? Right? Now, to visualize this, imagine this vertical line here as my arm, like this. Right? And then let's just say that we look at carbon 2, which is this bond right here. Right? Let's say this is the OH right here. OH is going to the right side. If I like topple it 90 degrees clockwise, right? Like this, you notice how the OH is on the bottom? Whereas if you look at carbon 3, the OH is on the left side. So if I topple it 90 degrees clockwise, it's facing up. Right? So everything on the left side right here is up. Everything on the right side right here is down. Right? So when I close the ring here, I can do it in Haworth projection or chair confirmation. I'm going to do it in Haworth projection first, which you would draw it out like this, and you can number it like this. Where this is going to be 1, this is going to be 6, 2, 3, 4, 5, right? This 1 right here is this anomeric carbon. This 6 right here is this oxygen. This right here is the new bond between 1 and 6, or the story not, because there was no bond between 1 and 6 before. Right? Imagine this oxygen here comes to attack this carbonyl, push the double bond to oxygen like that, creating this new bond right there, closing the ring, making a 6 ring. But you know how, like, when this 6 oxygen atom here attacks this carbonyl carbon, we push this double bond into the oxygen, which becomes an O minus. That O minus will become an OH, which we'll draw later. Now let's focus on carbons 2, 3, 4, 5. At carbon 2, and we're gonna draw the alcohols here. I'm gonna leave the hydrogens as invisible. At carbon 2, will the alcohol be at the top or bottom? Based on this special projection right here. Would it be up or down for carbon 2? So we see alcohol at carbon 2 is at the right side, so it's going to go down, because if you topple it like this, alcohol is going to go down. At carbon 3, alcohol is going to go up. Carbon 4, alcohol is going to go down. Carbon 5, it's not an alcohol, but it's going to be a CH2OH. And I'm gonna draw like that, because this is the CH2OH. For this last car center, the best way to figure out if the alcohol is up or down is to see if it's on the right side or left side. Like if you look at this carbon 2 over here, we know the alcohol is down because the alcohol here is on the right side of this line. But at carbon 3, you know how the alcohol is on the left side of the line? That's why at carbon 3, the alcohol is going up.
I meant for like the
Uh-huh.
CH to OH group.
Yes, yes.
Because I know some of them they draw the wrong down, so that's when they're on.
The L sugar. If the CH2OH is going down instead, then you know that that came from an L sugar. If the CH2OH is going up, that came from a D sugar. Yeah, so that's good, that's good. Yeah. Now, everything is going to be the same because we're going to get actually two different products here. Except at the anomeric carbon, which is this red dot carbon right here, which was the carbonyl carbon. Because we know this anomeric carbon here is sp2 hybridized, which is flat and planar. So when the alcohol comes into attack, it gets attacked on the top side or the bottom side, making the OH go on the top or the bottom. And these are anomers of each other, right? Where they defect the anomeric carbon. If the CH2OH on the other side and anomeric alcohol are cis to each other, we call that the beta anomer. If the CH2OH on the other side and anomeric alcohol are trans to each other, we call that the alpha anomer. Like that. Okay? Wait. Yeah. Now that's Howard's projection. Do not draw the Howard's projection like this. Because in Howard's projection, we get all axial bonds, all straight up or straight down bonds. Right? If you draw like this, you cannot clearly see the straight up or straight down bonds for these bonds right here, right? Because this bond is getting in the way. Right? But when you draw it sideways like this, you can easily see the straight up or straight down bonds. Right? So that's a common mistake where people draw the Howard's projection in this straight up position like that, but do not draw it like that. Now we could just convert this into a chair confirmation, like this. Where this is going to be the anomeric carbon right there. This is going to be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, before we do that, let me review you guys the chair confirmation here. The axial bonds are going to be straight up or straight down. And the way that I remember that is that I start at the top left corner and it goes straight up. And it will alternate between up, down, up, down, up, down. Because this is up, the next carbon would be down. Next carbon up, next carbon down. If this was a carbon, it would go up. But because it's not a carbon, we don't draw anything there. But imagine it's going up, next carbon down. So those are the axial bonds. It will alternate between up, down, down. In this specific order. Now equatorial would be on the opposite direction of axial. So focus on this carbon here. Because axial is going up, equatorial has to be down because they're opposite direction. And they're going to be down parallel to the second bond that you do not touch. So it's going to be parallel to this one and this one because like these are the bonds directly attached to it. We ignore those bonds. We look at the next set of bonds. It's going to be down that way, up, down, up. Right, so those are the equatorial bonds for this chair confirmation, which we can now translate this into this from here. Okay? So I'm just going to draw axial, up, down, up, down, up, down, up, down, up, down, up, down. Equatorial, opposite direction than axial, parallel to the next set of bonds. That, right? Okay. Now, let's look at the beta anomer. And look at carbon 1. Where would the alcohol be at for the chair confirmation? The axial bond or the equatorial bond? Based on this Howard projection here.
Where was something fire when
Equatorial, right? Because we see alcohol is going up, and we have to ask ourselves what bond is going up, axial or equatorial? The bond going up here is equatorial, correct? And this here is going to be a hydrogen, which I'm going to erase because that's invisible inside,
that?
right? But then you could just look at that if you guys want to template of the chair confirmation axial or equatorial bonds. How about for carbon 2? Where would the alcohol be, axial or equatorial? Equatorial, correct? Because it's going down. That erase this bond. Carbon 3. Equatorial as well. It's going up. Carbon 4. Equatorial again, correct? 5.
So it would be PC.
So 5, the CH2OH is going up. And 5 here, the one going up is also equatorial. Because axle's going down here. So C2 OH, not an OH. So you're gonna see glucose referred to as the all equatorial sugar. Because except the anomeric carbon. Like ignore the anomeric carbon. All of these other bonds here are equatorial. Right? It doesn't have to be like this. Because like if it was like D-mannose or D-galactose or D-ribose, ribulose, then like some alcohols can be axial. But D-glucose, every other carbon besides the anomeric carbon is gonna be equatorial. Right? Copy and paste the entire thing. And this over here.
It's gonna fire more.
Except the anomeric carbon. Because that's when it
Fire more synthetically into your heart and then it's gonna reduce
Now at the alpha anomer, the alcohol is going down, and the thing that's going down here is axial with the alpha.
well
Anomer.
after the barrel.
So this is the alpha anomer, this is the beta anomer. Which one do you guys think is more stable, beta or alpha anomer? Yeah, beta anomer. Because in molecule A, we talked about 1,3 diaxial strain, where every bond here is equatorial, right? It avoids their agents. Whereas the axial one here has 1,3 diaxial strain. Not yet. So in nature, this is like 64% approximately. This is like 36%. So that's just a conceptual thing. Like Levens will ask which one's more stable, the beta or alpha anomer, and the answer would be beta anomer because it avoids the 1,3 diaxial strain right there, like that. Okay. Yeah.
So for the other sugars, how would you know?
Yeah, so other sugars will have different configurations right here, right? So let's say the OH for carbon 3 was on the right side, right? 1, 2, 3. If it's at the right side, it's going down. So what one is going down there? Equatorial or axial? So that's when the OH will be axial right there. Yeah. Now I will be having another 4-hour final review session tomorrow on Zoom, which can be found right there if you guys are interested. But that's gonna be it for today. And good luck on the final on Monday, I think. Or when is it? Friday. Okay, that's good. You guys have a whole week. That's good.